Assalamualaikum and hi everyone. In this video, I want to explain to you about the mechanism of dehydration of alcohol, one way to prepare alkene. So I will use the simple example first before we go to the more complicated one. So this is one type of alcohol. This is 1-butanol reacted with concentrated H2SO4 heat. This is the reagent for dehydration of alcohol. And it will produce two products here. The first one is minor product. The second one is a major product. We will start with the first step. Okay. First step, name as protonation of alcohol or OH group. Protonation means adding proton. Proton here is referring to the hydrogen. Okay, where comes the hydrogen? Look at the reagent here. We use the concentrated H2SO4. So in the first step, the H2SO4 will involve to make the protonation of the OH group in the alcohol. So let's look at how it happened. First, I will withdraw the alcohol involved. Okay, and I will add the H2SO4 here, but I will write it as this structure as it will be easier for us to show the bond cleavage in the reaction. Okay, so look at the OH group. It has a lone pair at OH group. So OH from the alcohol, it will attack the hydrogen from the acid catalyst. So when it attack this hydrogen, this OH bond will break. So one bond consists of 2 electrons. These 2 electrons will go to the O. So what we will get here is we will have CH3, CH2, CH2, 2O. Okay, and H is protonated to this hydroxyl group. Okay, and it will become positively charged plus HSO4 minus. It is the acid catalyst that already break the OH bond, or the proton or hydrogen ion here has already attached to this hydroxyl group. So we will get the protonated alcohol at step 1. Okay, now we go to step 2. Step 2 named the removing H2O and formation of carbocation ion. This is step 2. Okay, before that, I will copy back the species or the ion form or the protonated alcohol form from step 1. I will copy back. Okay, I expand the bond here. The bond of the carbon, the neighboring carbon of this protonated hydroxy group, because it will easier for me to show the bond cleavage after this. Okay, if you look at the structure, this is actually H2O. H2O that attached to C. And H2O, when it attached to C, it is unstable and it will automatically break the bond between O and C. So in step 2, this CO bond will break and 2 electrons will go to this O. Okay, what we will have after this CO bond break, this H2O will be out. That's why for this step, named as removing H2O. Okay, so what happened when the H2O already out from the ion? So we will have CH2. Okay, this C already lost the H2O. Now it has become the carbocation ion plus H2O. So for the second step, it is removing H2O and also the formation of carbocation ion. That is for second step. Alright, class. This is one important thing in step 2. Look at the carbocation ion form. Okay, for step 2, you must always note about the carbocation ion form and the neighboring carbon and its neighboring carbon. So look at this carbocation ion. It is primary carbocation ion, but the neighboring carbon here is secondary carbon. Okay, so which one is more stable? Of course, secondary carbon, right? So when the neighboring carbon of the carbocation ion is more stable than the carbocation ion, so there will have possibility of rearrangement occur in this step. Okay, so now I will show you the rearrangement. I will copy back this carbocation ion and I will expand the neighboring carbon because we want to show the movement of electron. It will easier for us if we use the expanded structure. Okay, what will happen here, class? This hydrogen from the secondary carbon will move to this carbocation ion. Okay, so we will have CH3, CH2. This one has been CH3. Now the carbocation ion here has become the secondary carbocation ion. This is primary carbocation ion. This is secondary carbocation ion. This process, we call it as 1,2 hydride shift. This is one kind of rearrangement in the organic reaction, organic chemistry reaction. Okay, 1,2 hydride shift means the hydride shift to this carbon so that we can have more stable carbocation ion. Okay, that will happen in step 2. So always remember, after the formation of carbocation ion, you have to look at the neighboring carbon. If it is more stable than that carbocation ion, so has possibility to undergo rearrangement to form more stable carbocation ion. Alright, we go to step 3. Step 3, name deprotonation of neighboring carbon. We will remove proton of neighboring carbon from the carbocation ion. Okay, I will copy back this carbocation ion form from step 2. Okay, to make it easier, you expand the bond of the neighboring carbon of the carbocation ion. Like what I draw here, this is the carbocation ion. So I will expand the bond in this carbon and this carbon because it will easier for me to show the bond cleavage in the mechanism. Alright, so which species will involve in the deprotonation? Okay, look at step 1. Okay, step 1. It already have HSO4 minus and we know that this is our catalyst, right? Catalyst, it will remain after the reaction. Okay, so in step 3, the HSO4 minus from step 1 will involve again. So here, HSO4 minus, this HSO4 minus will get back its hydrogen so that it will remain as H2SO4. Okay, so the arrow that you should show in this step is from this HSO4 minus. Okay, now I will show this attacking of HSO4 minus to this hydrogen first. We have two kind of hydrogen, two kind of neighboring carbon. This is primary, this is secondary. So that's why we will have more than one product. But this arrow I want to show for the first product first. Okay, so what we will have here, when this HSO4 minus attack this hydrogen, CH bond will break. So when CH bond break, these two electron will go to this side, to this bond. So we will have our first product, CH2, C double bond at this carbon. Okay, we will have our first product. So this one, we remove or we do deprotonation of primary hydrogen. Remove primary hydrogen. Okay, so we will get this product. Okay, now I want to show you the second product. Okay, still HSO4 minus that involved. Okay, now we will show the attacking of this hydrogen. So from this O, it will attack this hydrogen and this CH bond will break. So two electron will go to the bond here. So two electron will go to the bond here. HSO4 minus will attack the hydrogen. This hydrogen, this is secondary hydrogen, and CH bond break, two electron will go to this side, and we will have our second product, which is CH3, CH double bond, CH, CH3. This one we remove secondary hydrogen. Okay, now we can see that at step 3 we have two product formed. Now we want to determine which one will be the major product. So we will apply the Sizef rule. Now look at this first. We will have a look at this CC double bond. This carbon have one alkyl group. This is H, not alkyl group, while this carbon has no alkyl group. So for this product, we only have one R group. Okay. How about this? We will look at this CC double bond. Okay. This carbon, we have one R group. This is not R group. This carbon, this is not R group, but we have one R group. So this product, we have two R group at the CC double bond. Okay. According to Sizef rule, the major product will be the most stable alkene, and the most stable alkene is the alkene with highly substituted alkene. Highly substituted here means the alkene with more R group. So we compare these two products, we can see that this compound or this product has more R group compared to this one. That's why this will be our major product, while this one will be our minor product. Okay, so that's all for the mechanism of dehydration of alkene. Let's I conclude it for the last time. So for the dehydration of alkene or elimination reaction involve 3 steps. Step 1 is protonation of alcohol. Step 2 is removing H2O and formation of carbocation. And step 3 is deprotonation of neighboring carbon. So it will involve the concentrated H2SO4 heat, and it will produce two products for this reaction, major and minor, and we will apply the Sizef rule to determine which one is a major and minor product. Okay, that's all class.